Lady Thomas from the University of Jacksonville. And this is session F014 for the evaluation that began. The title of our session is A Structured Approach to Inference in Introductory Statistics. And our presenter is Peck. Can you all hear me? Okay. Roxy is currently a professor emerita of statistics at Cal Poly. While at Cal Poly, she served as associate dean at the College of Science and Mathematics and chair of the statistics department. Roxy was made a fellow of the American Statistical Association in 1998, and in 2003 she received the American Statistical Association Founders Award in recognition of her contributions to K-12 and undergraduate statistics education. She's the author of several introductory statistics textbooks. Please welcome Roxy Peck.
Well, thank you very much, and thank you for coming out so early on the first day of the conference. I'm excited to be here. I'm going to, because they're recording this session, I'm kind of stuck to the podium here, so if I start to wander and then all of a sudden run back, you'll know why I did that. So anyway, well, the title of what I decided to talk about this year is an approach that's taken me many years to kind of think about and develop, basically it has to do with reflection on the introductory statistics course, the typical intro statistics course that we have at the university level. And if you think about it, in that course, and in either one quarter or one semester, we typically have 8 or more different hypothesis tests that we have asked students to master, 5 or more different confidence intervals that students have to deal with. And I've always known, we've always known that this presents some challenges for students. In particular, once we get to this part of the course where we just start doing, almost every day a new inferential method, it becomes very difficult for students to choose an appropriate method. They get mixed up in terms of what the requirements for the different methods are, and so knowing when the selected method is appropriate, what conditions they need to check, those kinds of things are difficult for students. And then they have difficulty sometimes in figuring out the nature and the scope of conclusions that they can draw at the end of all of these things. And so what happened is, in starting to think about this, it actually happened about 5 years ago. I had a football player in my office in spring quarter, because our football players don't take statistics in the fall quarter. They're timed well with their sport, and who was struggling with the introductory statistics course, and they had just started their spring training, and he had this great big football playbook with him. And and trying to help, trying to figure out how to explain things, I realized that in this playbook, I said, well, what is that? And he was describing his playbook and showed me, what was in the playbook. And I realized this is somebody that's capable of learning all of these different complicated plays, remembering them, and then knowing how to execute them on very short notice on the field. And it kind of got me into this playbook analogy, and say, well, what we're thinking about doing in statistics is developing students' statistics playbook. And if you think about all the inferential methods as being the plays, then the things that they need to be able to do is to choose an inference method, which is like figuring out which play in the playbook you need to call at a particular time. Then they need to carry out the analysis, that's the executing the play, and then they need to draw conclusions and communicate those conclusions, and that's kind of like the commentary, the person that says what just happened and what does that mean, is like the commentary in a game. And so I thought, well, maybe this is an approach to start thinking about. And in talking with this student and saying, well, how do you choose a play? Now, he doesn't get to choose the plays when he's playing football, but how do you think your coach chooses which play to call at a particular time? And he had a very clear idea of it depends on the circumstances, what down it is, where we are on the field, and all of these other things that go into the decision of what might be an appropriate play in a given situation. And so it was kind of thinking about it in that perspective. I know it's kind of an odd thing, but thinking about that in that perspective of why is this student who's obviously bright, who can master this complicated game of football and all the different plays at that level. Why is this student struggling with these ideas that have kind of a clear analogy in statistics? And it kind of made me reflect on how we teach some of these things, and to think about trying to come up with a different approach that makes these kinds of decisions that we want students to make more explicit. I think that in a lot of what we do in the introductory statistics course, a lot of these things are hidden. They're not made explicit. We just kind of expect students to pick them up along the way. As we introduce a new method and we say, oh, by the way, you use this when, we kind of expect them to be able to integrate that into a systematic way of evaluating the situation and to kind of incorporate that, and I've never really been very explicit about it. So what I'm going to share with you today is kind of what kind of came out of the thinking hard about this conversation with this student and how it's changed the way that I approach teaching inference in that introductory statistics course to try and deal with some of the things that we're asking students to do and help them to see it in a more systematic way. So the first thing that I set out to try and do is to look at this idea of how do you select a play. And as I said, the way that I used to do it is we'd start with a hypothesis test for one proportion. We might talk about, well, you use this to test a hypothesis about a population proportion, and then we would go on, and when we introduce the next one, we might make that comparison to how it related to the other one, but we kind of expected that by describing a situation where you would use this, that they would integrate it systematically. So to try and make this explicit, I said, well, from the football analogy point of view, if we said, well, the coach has to take all these different things into account in terms of selecting a play, what are the things that students need to take into account in order to select an appropriate statistical method? And it came down, I kind of boiled it down. I started with 5 questions, but I didn't get a nice acronym with that, so I ended up with 4 questions because I wanted something that students could remember. And to say, here are 4 things that I want you to think about before you even start a problem. And now we actually talk about all these 4 things and practice answering these questions before we look at any statistical inference methods, because you don't really need the methods yet to be able to answer these questions. So the things that I want students to think about are what type of question are they trying to answer, what type of study are they looking at, what type of data are they dealing with, and then how many samples or treatments. And I'll talk about each of these individually in just a minute. But the idea is that if a student could answer these 4 questions, that this actually would determine what statistical method they should consider when they try and analyze the data or answer the question that's been posed. So looking at this, the first one is question type, this is where I've asked, and I never used to do this with students before, but a key thing in terms of selecting a method is we have both confidence intervals and hypothesis tests in the introductory course. And they need to decide, is this a question that's best answered? If it doesn't say calculate a confidence interval for, or test this hypothesis, I want them to be able to look at a question that's being posed in the context of a study and decide, is this something that requires estimation or is this something that requires hypothesis testing? And so we talk about the difference between estimation problems and hypothesis testing problems, with the idea that in an estimation problem, the goal is to learn to use data to learn about the value of some population characteristic, whereas in a hypothesis testing problem, the goal is to decide whether data support a particular claim that's being made about a population characteristic or maybe how two populations compare. But this is something that we can talk about, and I never used to talk about this explicitly, and to ask students to look at this and try and answer this question before they did anything else. So there are two handouts. One handout that you have is a copy of the slides, but the other handout is a set of examples that I use with my students. And so I thought I wanted to kind of show you the kinds of things we look at before we get on to the actual inferential methods themselves. And the first example that I would like you to look at is example 1 on the handout that's called Deception in Online Dating. And I'll give you just a minute to take a look at that example. It's from a study that looked at whether people thought that people were honest when they put their profile on these online dating sources. And so there's a short description of the study, and then you can see that there are 3 questions that the researchers hope to answer from this study. And those 3 questions are: what proportion of online daters believe they've misrepresented themselves in an online dating profile? What proportion of online daters believe that other people frequently misrepresent themselves in their online dating profile? And then they also had another question that they wanted to know if people that placed greater importance on developing a long-term face-to-face relationship were more honest in their online dating profiles than people that weren't looking for a long-term relationship. So having students read this and look at these 3 questions, we can then take a look at the 3 questions that are posed here and try and answer that first, the Q part of the 4 questions. To answer this question, is this a question that's an estimation problem, or is this a question that's a hypothesis testing problem? And so if you look at that first question, they wanted to know what proportion of online daters feel that they've misrepresented themselves in an online profile. Is that an estimation problem or a hypothesis testing problem? Okay. Yeah, that's an estimation problem. And you can see by answering this, as soon as they say estimation, they're going to be moving off toward thinking about confidence intervals or point estimate and margin of error, as opposed to a hypothesis testing situation. Question 2 asks about what proportion of online daters believe that other people have frequently misrepresented themselves. That's also an estimation question. But question 3, are people who place a greater importance on developing a long-term relationship more honest in their profiles? Okay, that's a hypothesis testing situation. To answer that question, I have to use the data to see if it supports that claim. So that's a hypothesis testing situation. And we can talk about this before we've ever looked at the different confidence intervals and the different hypothesis tests. And this is something that you could actually start very early on if you use real studies, even in the parts of the course where you're dealing with descriptive statistics. You can start talking about, we're summarizing the data here, but if we wanted to use the data to do this next thing, would that be estimation or a testing situation? So that's the first thing that I want students to think about when they look at a new problem. And this immediately will kind of head them in one direction in terms of methods. The second question that I want them to think about is the study type. Data typically that we deal with in the introductory course either comes from sampling, selecting samples from some population, or it comes from an experiment. This is something that the emphasis on the difference between sampling situations and experiment data that comes from experiments is something that we used to, I would say 15 years ago, we just totally ignored this. We introduced statistical inference as saying inference is what you do when you want to generalize from a sample to the population from which the sample was selected. We talked about comparing 2 populations. It didn't occur to me till much later, which is embarrassing but true, that then when you actually look at a lot of the data that we use in our examples and our exercises, it wasn't data that came from sampling from a population, it was data that came from an experiment. Where you had a group of people that were assigned to experimental conditions, and we collected data and we wanted to compare. And so we kind of expected students to be able to do that, but we never really talked about it much. Then I would say maybe 10, 15 years ago, we started saying, you know, this is a problem, and no wonder students can't take data from an experiment and do correct interpretations of the results once they've done their hypothesis test or calculated a confidence interval, because the only thing we've talked about is the idea of sampling from a population. And so then we said, well, we need to address both, but the way I approached it, and I think the way many other people approached it who tried to say, okay, I need to acknowledge experimental data, is to try and do them both at the same time. To say, okay, so you use this test, and then you have to say things like when you're trying to compare two population means, or you have an experiment and you're trying to compare two treatment means. And I found, you know, I felt better about what I was doing, but I found that was equally confusing to students because you're trying to do, you know, trying to do both things at once. And so where I've kind of come to in this last 5 years is to early on make the distinction. Okay, is this data from sampling? Is this data from an experiment? To acknowledge that I'm going to do different things. I may use that same two-sample t-test, but the hypotheses are different. The conditions I need to check are different. It's no longer random sampling, it's random assignment, those kinds of things. And the conclusions that I draw at the end are different. And so rather than try and do them together, I've come to this saying, well, let me just at the beginning distinguish, is this sample data or is it experiment data? And then when I teach, I actually, rather than try and do them both at the same time now, I've kind of come to the place where I just do sampling from a population, okay, initially, do it cleanly and thoroughly, and then separately address at the end, after we've done the hypothesis test, all in the context of sampling from a population, which is the easiest context for students to grapple with. Then I do a separate unit. It doesn't take long because you don't have to introduce any new tests or confidence intervals, but do a separate unit about now what do we do if the answer to this initial question was experiment data? Okay, how do things change? How do my hypotheses look different? How are the conditions different? How do I word my conclusions? They're going to be about treatment means or treatment effects as opposed to population means. And it doesn't take much extra, but by distinguishing early on and then saying, I'm only going to deal with this first case initially while you're learning the methods, and then we're going to look at how to deal with the second case, I found is less confusing for students. So that's why I put this as one of the kind of the key things that I want them to think about initially. So now let's take a look at the examples 2 and 3 on the other handout. And I wanted to kind of have you take a look at these 2 examples. These are 2 that I use with my students, and just to look at it with the lens of, is this data from a sample or is this data from an experiment, to try and answer that second question. So the example 2 is a study that was done by the Kaiser Foundation, and it was looking at media use among young children. They found that kids that have a TV in their bedroom tend to read less. And so they were interested in looking at the proportion of, these are really young kids, the proportion of kids between 6 months and 3 years old who had a TV in their bedroom, and they were also interested then in that same proportion for children that were 3 to 6 years of age. And the description basically describes they collected data from 2 samples of parents. I recognize they can't ask a 6-month-old kid if they have a TV in their bedroom. It's hard to do. But they collected data from samples of parents of children in these age groups. So what I'd want my students to do is to look at this and to recognize from this description that in that study, the answer to my second question is this is sample data. This is data they've sampled from some population. And that's going to have an impact on what I do in terms of the analysis that will follow. To compare that with a different study, there's the example, do you smoke after text? And this describes a study where they were looking at if people were trying to quit smoking, is it useful to have them get text messages periodically with kind of encouragement and reminders that, you know, that they shouldn't smoke. And so here, now this one's an easy one for my students to get because it uses the word experiment in the study description. But if you replace that word experiment by study, I would still hope that my students would look at this and be able to say they had 1,700 smokers. They were assigned at random to one of two groups. One group got text messages, the other group didn't. And then at the end of the study, they looked at, well, after 6 weeks, they looked at the proportion that had smoked in, let's see, it was in the previous week. So these were all people initially that were trying to quit smoking. And so in looking at a study description like that, I would want them to say, okay, well, this is data. I've got data. I have two groups, data from two groups, but this is data from an experiment. And so I'm going to do things a little bit differently when I go to analyze this data. Okay, does that make sense how these first two questions play out? All right, well, the next two questions that I like students to take a look at are more straightforward and more typical of the kinds of things that we've done all along. What type of data do you have? Is the data categorical or numerical? Oops, I'm missing a paren there, but is the data categorical or numerical? This is what's going to distinguish between methods for proportions and methods for means for our students. And I found that, again, by making it explicit, when I have categorical data and I'm choosing among the methods that I see in the introductory statistics course, I should be thinking about the methods that are appropriate for proportions as opposed to the methods that are appropriate for means. So categorical or numerical. And then I also in this step ask them to decide if it's one variable or two variable, because in the intro course we do handle bivariate data, both bivariate categorical data and bivariate numerical data. And so in this question they're going to be looking at, is it numerical or categorical, univariate or bivariate. So if we go back to those two examples that we just looked at, for the tuned-in babies example, if you look at that example and answer this question, it says they basically they were asking, well, they were looking at the proportion of kids that have a TV in their bedroom. They collected from 2 samples of parents. I think I cut off this sentence a little bit too early, but what they did is they asked each parent, does your child have a TV in the bedroom? So here, how would you answer? Is that categorical data or numerical data? Okay. Categorical data, and then they really just have, in this particular instance, one variable. Do you have a TV in the bedroom or not? So I'd want students here at this point to say there's one categorical variable. Okay. For the do you smoke after text, again, if you look at that one, what they've done is after 6 weeks, they have looked at whether the person had smoked within the last week. So is that categorical or numerical? Yeah, that's also categorical, and again, there's just a single variable. So that one we would answer one categorical variable as well. So the idea would be in this, like if you put these questions together so far for the do you smoke after text, that would be a situation that would be a hypothesis testing situation. It's data from an experiment, and I have one categorical variable. That's kind of where we would be at this point. And you can see how we're honing in. You know, if you think about the plays and the statistics playbook, with each question we're kind of narrowing in on a particular method, technique that they might use to analyze the data. All right, well, the last question is the easiest question, and obviously I have my animation wrong there because you're seeing the answer to my last question here. But the last one is they just need to know how many samples, if it's a problem where they have sample data, or how many treatments do they have. And so again, if we go back and revisit the 3 examples that we've looked at so far, deception in online dating, they had taken a sample of online daters, and so in that situation they had a single sample of online daters. For the tuned-in babies, there were actually 2 samples. They had a sample of parents of children that were 6 months to 3 years of age, and then a sample of parents that were 3 years to 6 years of age. And so there are 2 samples there. And you can see here again this is kind of the final thing that we need to choose a method. Am I going to basically use a 1 sample or 2 sample method is what we're looking at in this particular question. For the do you smoke after text, that's a situation where again they're comparing 2 groups, the group that got text messages and the group that did not get text messages. But because that was experiment data, what they really have is 2 treatments. You can think of it as 2 samples, but it's really they have 2 treatment groups from that for that particular experiment. Okay, does that make sense? Now, it seems like a lot for students to remember, to try and learn these questions. But what I found is that by doing this and then doing it consistently, by talking about this ahead of time, so we actually go through all of these studies and a couple others that you'll see in just a minute before we've done any inference. And it doesn't take really much longer because we've already talked about some of these things initially. Early in the quarter, we would have talked about the sampling, how to select a sample, and some very simple design of experiments kinds of things. So you're not having to introduce those things here. So it doesn't take a huge amount of time. I mean, we've just been talking for 20, 25 minutes. It's something that you can do in a kind of a single day if you've already introduced these ideas ahead of time. And I found that it really helps them structure their thinking. And then if I'm consistent from here on out in the course, and every time I put up a new example, we answer these questions, they do get to where they have the QSTN as a way of kind of remembering that there are 4 things, but they get in the habit of answering these questions before they just, charge on to a method. I know some of you have graded for the AP statistics exam, and there are situations where that students look at it and they see 2 columns of numbers, and they've already started to enter the columns of numbers into their calculators, and then they're starting to think, what do I do with 2 columns of numbers before they've ever even read the question, and so they're motivated more by those kinds of triggers. Oh, this is 2 columns of numbers, so it must be a paired t-test, or because they're listed this way and not this way, and so I'm trying to get them away from that kind of thinking to say, these are the questions I need to answer first. Yeah, that's a good question. I think that you could do that, although you might then have to wait until after you've introduced a few methods. You could probably do it before you've done all 8 hypothesis tests. But maybe if you start with, depending on whether you start with means or proportions, if you start with inference for proportions, after you've done 1 proportion and then 2 proportions, and then maybe as you introduce 1 mean, you could have them, I think they could probably come up with all of them, although they might not get the study type, the sampling versus experimentation clearly. So I think it would be interesting to yeah, no, but I think actually it would be, I think you could do something sort of like that in the sense of you could start with this, these are the questions I want you to think about, and then after you've introduced a few methods, you could say, so why are these the questions that we're looking at, and get them to say, why do I need to answer that first question before I pick a method? And the same, on the data type, why do I need to think about, is it categorical or numerical? Well, once they've seen methods for proportions and methods for means, they can say, oh, well, that's what makes the difference between, when I would choose this method versus that. So I think maybe you could have them reflect on that after, might be a good strategy. All right, other questions or anything, other comments or anything at this point in time? Yeah. Mm-hmm. Mm-hmm. Yeah, and I agree. And I think these are things that we always thought about. But I guess I felt after now it seems obvious to me, so I feel guilty that for so many years that I just never made it explicit. And you're right. I think by telling students that you have to answer these questions first, it does force them to read the question and read it carefully before they do anything else. And that's something that that in itself is beneficial. I know there's a lot of resistance. I mean, sometimes we hear, you know, that statistics problems or problems on the AP exam or problems in statistics textbooks, they're just too wordy. You know, why are they so wordy? And part of it is that they have to be wordy, you know, because in statistics the context is so important to doing data analysis. And so, yeah, you can ask a simple artificial question, but then what you're testing is, can they do the mechanics? And the mechanics are the easy part. You know, and if I were going to let one part go, that would be the part that I would be most comfortable letting go, because that's the part that can be, you know, can be done by a $69 calculator without knowing much else. So I used to tell students that they ought to, before, when I would do workshops for AP teachers, the advice I'd give is tell your students that they should never pick up their calculator until they know what they're going to do with it. And then they have to know that when they set the calculator down, they're not finished. You know, that there's still a lot more to be done. Because I think that's trying to get at that. You know, the context gives the problem meaning. I would argue that, you know, calculate the standard deviation of the following 6 numbers is not a statistics question. Even though it has the word standard deviation in there, it doesn't become a statistics question until those numbers are put in a context, because it's the context that gives it meaning and that allows you to figure out what that standard deviation is telling you. The calculation part is just an arithmetic, essentially an exercise in arithmetic and a little bit of algebra potentially, you know, but it's basically not a statistics question until it's put into a context that gives it meaning. And that makes it wordy, you know, and so when people say, oh, statistics books have too many words, I say, well, you know, I go back to that movie Amadeus when they said Mozart's music has too many notes, you know, so it's, you know, it needs, there's a reason that it has so many words, and so I've given up apologizing for that and just saying, yes, isn't that, I say now they say statistics has so many words, and I say, yes, isn't that great? So, but I'm not sure everybody buys that at any rate. Other thoughts? All right, well, I've got 2 other examples that I wanted you to take a look at. And so, whoops, I thought I had gotten good at my animating my slides, but evidently not. I guess we'll get all the questions up here at one time. So there's an example 4 on that handout called My Funny Valentine. And so this would be kind of putting it all together here and ask you to kind of look at that My Funny Valentine example and answer these questions. So I'll give you just a minute to read that, and then we'll come back and try and look at the answers here. I saw recent data here. This is about Valentine's Day, but there was a recent article in the newspaper. I may have to update this example that also surprised me, that people buy Halloween presents for their pets as well. So, although I have to confess, I did buy a Halloween toy for my dog, so I guess I shouldn't laugh at that. So. All right, so here, My Funny Valentine, it's a survey that was done by the National Retail Federation of Consumers, and they asked, do you plan to spend money on a Valentine's Day gift for your pet this year? And they were interested in learning about the proportion of U.S. adults that plan to buy a gift for their pet for Valentine's Day. So if you were going to answer these questions, would you consider this an estimation problem or a hypothesis testing problem? Okay, estimation. What would be an example of a hypothesis test? If I were going to change the last sentence there, Can you ask a different, could you say they were interested in, and what could you say that would make it an estimation, a hypothesis testing problem? I'm sorry, what? Yeah, one way you could say they did this survey in 2 years and they want to know if the proportion changed from this year to last year. You could ask a question about they wanted to know if a majority of adults with pets plan to buy a Valentine's Day gift for their pets. So again, we could talk about how that would change, but the way this is currently worded, you're right, this is an estimation problem. Is it sample data or experiment data? Okay, sample data, they've taken a sample of pet owners. One variable or two, and categorical or numerical? Categorical, they just, are you going to buy a gift for your pet or not? So categorical, and one variable, at least the way that's described. They probably ask other questions on the survey, but this particular description would be one categorical variable. And how many samples or treatments? Yeah, here they just have one. If we made the change that you had suggested to make it a hypothesis testing problem where they were comparing this year to last year and had done samples in each year, that would be then we'd have 2 samples on that situation. All right, another example, the last one on your handout there, example 5, about cell phones. It's a study that investigated whether talking on a cell phone while driving has an effect on response time. It says the subjects were assigned at random to one of 2 conditions. They were either talking on a cell phone while driving or listening to the radio while driving. And they were driving in a simulator. They were told when a light changed from green to red that they should step on the brake as quickly as possible, and they measured the response time. And the researchers then were interested in determining if using a cell phone while driving results in a slower reaction time. Right. So description of a study, estimation or hypothesis testing? Hypothesis testing, because the question that's being asked is really a claim, would involve testing a claim that using a cell phone results in a lower reaction time. Sample data or experiment data? Okay. This is experiment data. Okay. One variable or 2, categorical or numerical. Okay, one variable, response time, categorical, numerical. Okay. Numerical, so response time, so this would be 1 numerical variable, and then how many, in this case it would be how many treatments, because we've answered experiment data, how many treatments? Yeah, be two treatments, because we've got this talking on a cell phone versus listening to the radio. All right. So we've got the answers to these questions, and then, so like I said, I spend basically a day or so doing this, and then the question would be, now what? So the way that I use these questions is now, first of all, each time I introduce a new method, we talk about what answers to these questions would lead you to this method. Okay, so now we're introducing the one sample test, hypothesis test for a proportion, and we can say you would use this if you have sample. Well, if it's a hypothesis testing situation, you have sample data. You have 1 categorical variable and 1 sample. You know, that it's those choices that would lead you to this particular method. And then again, with every example, we answer these questions and say, and that's what tells me that it's this method. And then you'll see I put at the end of the handout with the examples, you'll see a table that I use with my students. This has, it doesn't, I cut it off here so that it would fit on one page, so it doesn't have the chi-square test that we typically do here. But you can see that with this table, it's based on the answers to these questions, and then what method that you would consider as your method for moving forward to answer that question. And so, like I said, what I've tried to do is make this process explicit, and it's embarrassing that I always just, each time you say, okay, well now we're going to look at what happens when you have two samples and the question is about means, and then we were on to the method, and I kind of expected students to integrate this into a systematic approach of their own. So in terms of the statistics playbook analogy, this business about answering the 4 questions is what I consider the piece that looks at selecting the play, and then each time we add, eventually I'd love to have, I haven't gotten my computer savvy friends to do this, but I'd love to have an online where I actually have these plays that they could add to, a student could say, okay, now I've mastered this one and I get to add it to my playbook. But then these are the questions that would kind of be at the top that say, okay, this is the play I'm going to choose under these conditions. So that kind of gets you through the selecting a play. And then the next piece is, how do I carry out the play? And so I've looked at trying, again, to be systematic with this as well. And to look at, once the play's been selected, how do I actually carry out the play? And so what I have kind of tried to do with students is to say that all of the plays in my statistics inference playbook, all of the plays have 5 steps. Okay. And for estimation problems, to try and emphasize that these steps have a lot of commonality, for estimation problems, I'm using the EMC cubed, that's their acronym for remembering those 5 steps, and you'll see what those 5 steps are in a minute. And for hypothesis testing, we have this HMC cubed, and I've tried to, I think I've always had, or I don't know always, but for many, many years, given students a systematic approach for hypothesis testing, and it's not uncommon to see in textbooks, the 5 steps for hypothesis tests, or the 7 steps, or the 9 steps, depending on, how it's broken out. So this idea of having a systematic approach for carrying out a hypothesis test to make sure you get everything there is not something that's a new idea. But one of the things I noticed when I started working on AP exams, where checking conditions is such an important thing that they emphasize there, is that first in the early years nobody checked conditions for hypothesis tests, but then people started getting better. They got more systematic. They started getting better about checking conditions or assumptions in hypothesis tests. But then you'd give them a confidence interval problem, which has essentially the same conditions or assumptions as the hypothesis test, and nobody would do it there. And I realized it was because we would give them this, our 7-step process for hypothesis tests, and we didn't have a 7-step, although we could easily have, but we didn't have a corresponding process for estimation, for doing confidence intervals that helped them make sure that they got everything that they needed. And so in trying to think about, okay, well now maybe I need to be more systematic about what I'm having students do with estimation problems to make sure that they realize that they need to do these other things as well as just the calculation and interpretation. Then what I wanted to do is emphasize that it actually is a very similar process. I didn't want to go off to something that's completely different, because really all of the steps except the initial one is the same. And so that's why you see these 2 acronyms here. The MC cubed part is the same for both. It's just how you start off. And I know you probably can't read this on your little tiny handout, but if you email me, I'd be happy to send you a bigger version of this slide. But this is what the process looks like for estimation, and you can see each step is detailed. And so I ask students to kind of learn this process. The E part goes with estimation problems, and it's explaining what population characteristic you plan to estimate. So it's kind of defining, saying I need to estimate the population proportion, and to define that population proportion in the context of the problem. The other steps, method, selecting a potential method, that's where my 4 questions come in. That's the selecting a play from the playbook. and that's going to be determined by the answers to those questions. C is the first C is for check, so that's checking to make sure that the potential method is appropriate. And so that's the checking the conditions or the assumptions that are necessary for the method that you've selected, because even though those 4 questions might point me to a particular method, it still may not be, I may not have a sample size that's adequate, or there may be other things that say, even though this is the method I was thinking, it's not going to be an appropriate way to analyze this particular data. The second C is the easy one. That's the calculate step. That would either be hand calculations, or if you're using technology, that's the step that can be done with technology. But I also point out to students, notice it's only one of the 5 steps, that's not, because often they want to know, well, I had I wrote the right numbers for the confidence interval on my paper, how come I'm only getting a few of the points for this problem? And I said, well, you did one of these things and you did the easy one. So, although I say, well, you kind of had the M, right, because if you use the right confidence interval, but I want to see all of these things. And then the final C is the communicating the results part. That's the going back, answering the question. It needs to be in context, and this is where you'd also acknowledge the risk, any risk associated, so risk of error in terms of hypothesis testing, talking about the confidence level in terms of estimation. And so you can kind of see here with this method, and if you go back to the playbook analogy, the selecting the play and the giving the commentator, the commentator saying what happened and what does it mean are kind of built into this process. But I find students kind of understand the playbook analogy if they know what a playbook is. So the one thing in using that analogy, what I've had to do, I actually stole some pages from my football players' playbooks that I could copy to show, and so I now use those. I kind of say, so this is what a playbook looks like, and we're going to develop your statistics playbook. I'm sure they wouldn't carry their statistics playbook around like the football player carries his football playbook around and be proud, show it to other people, like, look what I have. But it's something that they can resonate with. And I think the decisions are similar. I mean, I think the analogy, I haven't ever had anybody come up with something that's made me think that the analogy is really bad at this point. And then you can see the last, this is basically the process for hypothesis testing, and the only thing that's different is that first step, where instead of defining the population characteristics that you're going to estimate, the first step is defining the parameters and setting up the hypotheses. But then the other steps are the same. So again, a systematic approach, a systematic way to select a play, systematic approach to carrying out a play, and then the last step here is the way of providing the commentary on the play. So there's my analogy. I found I've been doing this for about the last 4 or 5 years, and I found that it has helped to. It seems like extra stuff initially when you're learning those questions and stuff, but it really has helped students to organize their thinking and gives them some guidance in some of these things that they were struggling with initially. Right, so I think we have just a couple minutes left for questions, but if you have any questions, comments, or suggestions, and my email, if you have any that you think of after this, feel free to email me. Yeah.
Do you allow students to use the table on their test?
I do.
Okay.
Yeah. So I do let them use the table on exams. But I think they still, I don't know that they have to refer to it as often. I think they're just kind of getting it in their heads. But yeah, I do. And that doesn't bother me. I'd rather have them use that systematic approach and get the right method than to try and go in an unproductive, unproductive direction. Other thoughts or questions? All right. Well, I really appreciate your coming out so early in the morning on a beautiful day, and I hope you enjoy your time at AMATYC. So.